In today's hyper-connected world, it's hard to imagine life without the internet. We rely on it for everything from communication and entertainment to education and commerce. But have you ever stopped to think about the intricate web of technology that makes it all possible? Behind the scenes, a vast and complex system of interconnected devices work tirelessly to bring us the seamless online experience we often take for granted. This system is known as a computer network, and it's the backbone of our digital age. The digital revolution, fueled by the rapid advancement of computer networks, has transformed the way we live, work, and interact with the world around us. It has created countless opportunities for innovation and progress, connecting people and ideas in unprecedented ways. But this digital transformation has also brought about new challenges. The power of computer networks lies not just in their ability to connect devices and transmit data, but in the transformative applications they enable. From the rise of e-commerce and social media to the advancements in telemedicine and online education, networks have revolutionized countless industries and aspects of our lives. Embarking on a journey to understand computer networks might seem daunting at first, but it's a journey well worth taking. Like exploring a new city, we'll break down this vast and intricate landscape into manageable parts, uncovering the key components and principles that make it all work. At the core, a computer network is a system of interconnected devices that can communicate and share resources with each other. These devices, known as nodes, can be anything from personal computers and smartphones to servers, printers, and even smart home appliances. The key is the ability to exchange data and work together, transcending the limitations of standalone devices. Before the advent of computer networks, devices operated in isolation. Information stored on one computer was inaccessible to others unless physically transferred using floppy disks or other portable storage media. This limitation hindered collaboration, data sharing, and overall productivity. The true power of a computer network lies not just in the physical connections between devices, but in the seamless flow of information they facilitate. This flow of information, often invisible to the end user, is the lifeblood of the network, enabling communication, collaboration, and the sharing of resources. Examples of computer networks abound in our daily lives, often working seamlessly in the background without us even realizing their presence. From the moment you wake up and check your smartphone to the time you stream your favorite show before bed, you're interacting with a complex web of interconnected devices. Often referred to as the information superhighway. The Internet is perhaps the most well-known and widely used example of a computer network. However, the Internet is not a single entity, but rather a vast and complex network of networks connecting billions of devices worldwide. To truly understand how computer networks operate, it's essential to delve into their fundamental components. Just as a building is constructed from bricks, beams, and mortar, a computer network is built upon a foundation of hardware, software, and protocols. As technology continues to evolve at an unprecedented pace, the landscape of computer networks is constantly changing, adapting to new demands and possibilities. From the rise of mobile computing and the Internet of Things to the advancements in artificial intelligence and cloud computing, the future of networking promises to be even more interconnected and transformative. Just imagine trying to navigate a labyrinth or maze without a map. You might wander aimlessly, encountering dead ends and repeating paths, unsure of how to reach your destination. Similarly, understanding the flow of data across computer networks can feel like navigating a complex maze with countless paths and interconnected components. The OSI model, developed by the International Organization for Standardization in the 1980s, the OSI model is often considered the theoretical gold standard for understanding network communication. It divides the complex process of data transmission into 7 distinct layers, each responsible for a specific aspect of network functionality. To fully appreciate the elegance of the OSI model, let's take a closer look at each layer, starting from the bottom, where data originates, and moving up to the top, where it's presented to the user. At the foundation, we have the physical layer, responsible for transmitting raw bits of data over the physical medium, whether it's copper wires, fiber optic cables, or radio waves. While the OSI model provides a comprehensive theoretical framework for network communication, the TCP/IP model, named after its 2 core protocols, reflects the actual architecture of the Internet and many other real-world networks. This model, developed in the 1970s, precedes the OSI model and takes a more pragmatic approach to network communication. While the OSI and TCP IP models might seem like competing approaches to understanding network communication, they are best viewed as complementary perspectives, each offering valuable insights into the complexities of networking. The OSI model, with its 7 well-defined layers, provides a comprehensive theoretical framework for understanding the different stages of data transmission. At the top of both the OSI and TCP/IP models lies the application layer, the interface between network applications and the underlying network infrastructure. This layer is responsible for providing services to end users, allowing them to access network resources, communicate with each other, and share information. Just below the application layer and session layer, we find the transport layer, responsible for ensuring reliable end-to-end communication between applications running on different devices. This layer acts as a dedicated courier service, taking data from the application layer, packaging it appropriately, and ensuring its safe and reliable delivery to its destination. As we delve deeper into the network stack, we encounter the network layer, responsible for addressing and routing data packets across interconnected networks. This layer acts as a global postal service, determining the optimal path for data to travel from its source to its destination, even if they are located on different networks. At the base of the network stack, we find the data link and physical layers, responsible for the actual transmission of data over the physical medium. These layers act as the foundation upon which all other network functionalities are built, ensuring that bits of data can be reliably transmitted and received between devices. To truly appreciate the power of network models, let's visualize how data flows through the layers, using the example of sending a simple email. At the application layer, you compose an email using your email client. Understanding the OSI and TCP IP models provides a solid foundation for exploring the vast and ever-evolving world of computer networks. These models serve as essential roadmaps, guiding us through the intricate landscape of network communication and helping us comprehend the roles of various network components. In the bustling metropolis of a computer network, data packets are the tireless commuters, constantly traveling between devices, carrying information, and enabling communication. But just as a city needs a well-designed transportation system to ensure the smooth flow of traffic, a computer network relies on efficient and reliable transmission media to transport data packets between its interconnected devices. For decades, wired transmission has been the backbone of computer networking, providing reliable high-speed connections that form the foundation of the internet and countless local area networks or LANs worldwide. These wired connections rely on physical cables to transmit data as electrical signals, offering a robust and secure way to connect devices over short to long distances. The world of wired transmission encompasses a variety of cable types, each with its own unique characteristics and applications. These cables can be broadly categorized based on their construction and the materials used, ranging from the familiar copper wires to the cutting-edge fiber optic cables that transmit data as pulses of light. While wired connections have long dominated the networking landscape, wireless transmission has emerged as a transformative force, liberating devices from the constraints of physical cables and ushering in an era of unprecedented mobility and flexibility. From the ubiquitous Wi-Fi networks in our homes and offices to the cellular networks connecting our smartphones, wireless technology has permeated every aspect of our lives. Imagine the air around us as a vast, invisible highway filled with countless lanes, each designated for a specific type of traffic. This highway represents the electromagnetic spectrum, a range of frequencies over which electromagnetic waves, including radio waves, microwaves, and light waves, propagate. Selecting the most suitable transmission media for a particular networking scenario is a critical decision that involves carefully considering various factors. Much like choosing the right mode of transportation depends on the distance, budget, and urgency of the journey. There is no one-size-fits-all solution, as each media type comes with its own set of strengths and weaknesses. As our reliance on computer networks continues to grow, so too does the demand for faster, more reliable, and more accessible transmission media. The future of networking promises to be shaped by advancements in both wired and wireless technologies, pushing the boundaries of speed, capacity, and reach. Imagine a bustling city with a complex network of roads and intersections, facilitating the movement of people and goods. Just as a well-designed transportation system ensures the smooth flow of traffic, a computer network relies on efficient switching mechanisms to direct the flow of information between devices. Imagine making a phone call. When you dial a number, a dedicated circuit or path is established between your phone and the recipient's phone, remaining open for the duration of the call. This is the essence of circuit switching, a traditional switching technique that has been the foundation of telephone networks for over a century. In contrast to circuit switching's dedicated connections, packet switching takes a more dynamic and efficient approach to data transmission. Instead of establishing a dedicated circuit, data is divided into small packets, each containing a portion of the data and addressing information. These packets are then sent independently across the network, like individual letters sent through the postal system, each finding its own way to the destination. The choice between circuit switching and packet switching often boils down to a trade-off between guaranteed quality of service and efficient resource utilization. Circuit switching, with its dedicated connections, excels in scenarios where low latency, constant bandwidth, and high security are paramount, making it ideal for real-time communication like voice calls and video conferencing. In the quest for the optimal switching technique, network engineers have developed hybrid approaches that combine the strengths of both circuit switching and packet switching. One such approach is virtual circuit switching, a technique that seeks to provide the guaranteed quality of service of circuit switching with the efficiency and flexibility of packet switching. As technology advances at an unprecedented pace, the demands placed on computer networks continue to grow, pushing the boundaries of existing switching techniques and driving the development of new approaches. The future of network switching promises to be shaped by the increasing volume of data, the emergence of new applications, and the need for faster, more reliable, and more intelligent networks. Just as cities and towns form interconnected networks across a country, computer networks themselves exist in a vast and interconnected ecosystem, each type serving a specific purpose and operating at a different scale. These networks, ranging from the local area networks, connecting devices in our homes and offices, to the global expanse of the internet, form the invisible infrastructure upon which our digital world is built. At the heart of many homes, offices, and educational institutions lies the local area network, a group of interconnected devices confined to a relatively small geographical area, typically within a single building or campus. LANs are the workhorses of local connectivity, enabling devices like computers, printers, and servers to communicate and share resources efficiently and securely. As organizations grow and expand their operations, the need to connect multiple LANs across a larger geographical area often arises. This is where metropolitan area networks, or MANs, come into play, bridging the gap between the localized connectivity of LANs and the wider reach of WANs. While LANs and MANs provide connectivity within a limited geographical area, wide area networks, or WANs, extend the reach of computer networks across cities, countries, and even continents. WANs are the backbone of the internet, connecting disparate networks and enabling global communication on an unprecedented scale. Just as choosing the right mode of transportation depends on factors like distance, cost, and urgency, selecting the appropriate network type for a particular application involves considering various factors, including geographical coverage, speed, cost, and security requirements. The true power of computer networks lies not just in their ability to connect devices within a single type, but in their ability to seamlessly interconnect different network types, forming a global web of communication that transcends geographical and technological boundaries. This interconnection is made possible by specialized networking devices that act as translators and traffic directors, ensuring the smooth flow of information between different network segments. The world of computer networks is constantly evolving, driven by technological advancements, emerging applications, and the ever-increasing demand for connectivity. From the early days of isolated local area networks to the global reach of the internet, network architectures have undergone significant transformations, adapting to new demands and paving the way for future innovations. In the bustling metropolis of a computer network, where countless devices exchange information at lightning speed, a common language is essential for ensuring seamless communication. This language, known as network protocols, defines the rules, procedures, and formats that govern how data is transmitted and interpreted between devices. At the heart of the World Wide Web, the vast repository of information and services that has transformed our lives, lie two fundamental protocols: HTTP, Hypertext Transfer Protocol, and its secure counterpart, HTTPS, Hypertext Transfer Protocol Secure. These protocols, like the tireless couriers of the internet, govern the communication between web browsers and web servers, enabling us to access websites, retrieve information, and interact with online services. Imagine browsing the web as visiting different shops in a bustling marketplace. In the early days of computing, sharing files between computers often involved physically carrying floppy disks or magnetic tapes from one machine to another, a cumbersome and time-consuming process. The advent of computer networks and the development of the File Transfer Protocol, FTP, revolutionized file sharing, enabling the seamless transfer of files between computers connected to a network. Imagine trying to find a friend's house without knowing their street address, relying solely on their name. It would be a daunting and likely fruitless task. Similarly, computers on the internet rely on numerical addresses, known as IP addresses, to locate and communicate with each other. In the early days of networking, configuring IP addresses for devices often involved manually assigning a unique address to each computer, a tedious and error-prone process, especially as networks grew larger. The development of the Dynamic Host Configuration Protocol, or DHCP, revolutionized network administration by automating the process of assigning IP addresses to devices on a network. Network protocols, like the instruments in an orchestra, work in harmony to create a symphony of seamless communication. Each protocol plays a specific role, interacting with others in a coordinated manner to ensure that data flows reliably, securely, and efficiently across the network. The world of computer networks is in a constant state of flux, driven by technological advancements, emerging applications, and the ever-increasing demand for connectivity. Network protocols, the rules that govern network communication, must adapt to these changing demands, evolving to support new technologies, improve security, and enhance performance. In today's hyper-connected world, it's hard to imagine life without the internet, a testament to the transformative power of computer networks. From the moment we wake up and check our smartphones to the time we stream our favorite shows before bed, networks permeate every aspect of our daily lives, connecting us to information, entertainment, and each other in ways that were once unimaginable. Beyond our personal lives, computer networks have revolutionized the business world, transforming the way companies operate, communicate, and compete in the global marketplace. From small startups to multinational corporations, businesses of all sizes rely on networks to streamline operations, enhance productivity, and reach new customers. Computer networks have broken down geographical barriers, connecting people from all corners of the globe and fostering a new era of global communication and collaboration. The internet, a testament to the power of interconnectedness, has become a platform for sharing ideas, fostering innovation, and promoting cross-cultural understanding. As technology continues to advance at an unprecedented pace, the applications of computer networks are constantly expanding, shaping the future of various industries and transforming the way we live, work, and interact with the world around us. From the Internet of Things, or IoT, to artificial intelligence, or AI, emerging technologies are leveraging the power of networks to create new possibilities and solve complex challenges. As we conclude our exploration of computer networks, it's evident that we live in a world increasingly defined by interconnectedness. From the mundane tasks of checking emails and browsing websites to the complex operations of global financial markets and scientific research, networks form the invisible infrastructure upon which our digital lives are built. Like threads in a vast and intricate tapestry, these networks connect us to information, resources, and each other, transcending geographical boundaries and shaping the way we live, work, and interact with the world around us. In today's digital age, understanding the fundamentals of computer networks is no longer a niche skill reserved for IT professionals, but an essential literacy for everyone. Just as we learn to read, write, and do basic math, we must equip ourselves with the knowledge to navigate the digital world confidently and responsibly. The world of computer networks is in a constant state of evolution, driven by technological advancements, emerging applications, and the ever-increasing demand for connectivity. As we look to the future, we can only imagine the transformative innovations and challenges that lie ahead. But one thing is certain: networks will continue to play a pivotal role in shaping the world around us. Our journey through the world of computer networks has only just begun. The knowledge and insights gained from this exploration provide a solid foundation for further exploration and discovery. Whether you're interested in pursuing a career in networking, delving deeper into specific networking technologies, or simply staying informed about the latest trends, a world of learning and exploration awaits.